Imagine we collected study hour data from 20 students. For each student, we recorded two things: their study hours and whether they passed or failed. We plot this on a graph. The horizontal axis is hours studied. The vertical axis is the outcome: 1 for pass, 0 for fail. Now, a new student asks, I studied for 5 hours. What is the probability I pass? This is a classification problem. Unlike a regression for salary or temperature, our target variable is categorical, restricted to two distinct possibilities, 0 or 1. To calculate a probability for this student, our prediction must stay within a fixed range. For the output to be valid, it must remain between 0 and 1. In linear regression, we estimate a continuous response using the equation y equals a plus bx. Here, x is the hours studied, a is the intercept, and b is the slope. Fitting a straight line to binary data creates a problem. It continues infinitely, predicting impossible probabilities like -20. We solve this by passing the linear score a plus bx through a transformation function, f, mapping it into a bounded probability curve. To respect the boundaries of a classification problem, we must replace the straight line output with a bounded curve. There are two common ways to create this S-shaped probability curve. Probit regression uses the cumulative distribution function, while logistic regression uses the sigmoid function. Both curves rise through the middle to produce probability-like outputs. Focusing on logistic regression, the formula is y equals 1 over 1 plus e to the negative a plus bx. Here, x is our hours studied, a is the intercept, and b is the coefficient. The symbol e represents the mathematical constant used in the exponential function. We can simplify this by letting z represent our linear score, a plus bx. This gives us the standard sigmoid form, y equals 1 over 1 plus e to the negative z. When the linear score z becomes a large negative number, e to the negative z becomes very large. This makes the denominator massive, causing the final output y to approach 0. If z is exactly 0, e to the 0 is 1, resulting in a probability of 0.5. As z becomes a large positive number, e to the negative z approaches 0, which forces the final probability y toward 1. The sigmoid function effectively converts any linear score into a value between 0 and 1, allowing us to interpret the result as a valid probability. We can also express this relationship in a different way by rearranging the sigmoid equation to isolate our linear score, z. First, we multiply both sides by the denominator to get y times 1 plus e to the negative z equals 1. Expanding that gives us y plus y times e to the negative z equals 1. We isolate the exponential term by subtracting y and then dividing by y. Finally, we invert the equation to remove the negative exponent, leaving us with e to the z equals y over 1 minus y. This ratio, y divided by 1 minus y, is known as the odds. It compares the probability of an event happening, such as passing, to the probability of it not happening. By taking the natural logarithm of both sides, we cancel out the exponential base e. This leaves us with z equals the log of the odds. This expression is called the log odds, or the logit. When we substitute our linear expression back in for z, we find that the log odds of the outcome are a linear function of our predictors. This derivation shows the core architecture of logistic regression. It maintains a linear relationship, but it does so in the log odds space rather than the raw probability space. We have a model structure, but we still need to determine the best values for the coefficients a and b to fit our student data. In linear regression, we typically minimize the sum of squared residuals. However, that approach is not used for logistic regression. Instead, we use log loss, also called cross-entropy loss. In this equation, y is the actual class, either 0 or 1, and hat y is the probability predicted by our model. If a student actually passed, y is 1. The second term of the equation becomes 0 and disappears, leaving the loss as negative log of hat y. If the student passed and the model predicts a high probability of passing, the loss is small. However, if the model predicts a probability close to 0 for a student who actually passed, the penalty becomes very large. If the student actually failed, y is 0. The first term disappears, and the loss becomes negative log of 1 minus hat y. Now, the model is penalized if it assigns a high probability of passing to a student who failed. Log loss ensures that the optimization process is driven by the distance between the prediction and the true class. The algorithm is adjusted most aggressively when a high-confidence prediction is furthest from the actual outcome. We can now see the complete pipeline. We take the input, calculate a linear score, transform it through the sigmoid to get a probability, and use log loss to find the coefficients that minimize our error. Returning to our 5-hour study example, the fitted curve allows us to estimate the probability of success. At 5 hours, the model indicates a high likelihood of passing. This makes logistic regression a classifier that provides specific probability estimates. We can use these percentages to categorize new observations based on the strength of the mathematical evidence. This isn't limited to one variable. If we add more predictors, the linear combination expands, and the S-curve becomes a multidimensional probability surface. Whether we use one predictor or many, the engine remains the same, a linear combination transformed into a probability scale. Logistic regression is efficient in practice. Once the coefficients are learned, the model can classify new records nearly instantly. It is quick to train and provides a measure of confidence for each prediction. It can also be extended to multinomial regression for problems with more than 2 outcome classes. However, the model has limitations. It constructs linear decision boundaries, which may not capture complex, nonlinear patterns in the data. It also assumes variables act independently, unless interaction terms are manually added. Finally, because the coefficients scale the log odds rather than raw probability, they can be difficult to interpret directly. Despite these constraints, the model remains a foundational tool. It connects the simplicity of linear equations with the requirements of probability-based classification. By calculating the probability of an outcome, logistic regression provides a rigorous framework for quantifying uncertainty based on observed evidence. For a student with 5 hours of study, it provides the most important answer: how likely they are to succeed.